Thank you all for coming. I'm Robert Wright, visiting professor of science and religion at Union Theological Seminary here. And this is a conversation that's one in a series of public conversations that are part of the Insight project that we just launched. In fact, the launch was a couple weeks ago. Some of you may have come to, there was a conversation about climate change with Amitav Ghosh. I've been asked by people who ask these things that if you feel like tweeting about this, you should use the hashtag Insight Project. Is that right? One word. I don't personally encourage tweeting, but there are people here who do. Our guest tonight is Brian Greene. I'm sure most of you are familiar with him. He's a professor of physics right here at Columbia, right next door. Also, best-selling author of a number of books, The Elegant Universe, Fabric of the Cosmos, Icarus at the Edge of Time, The Hidden Reality.
Very good.
Thank you. I practiced. The first of those, in addition to being a big bestseller, was a PBS series starring Brian, or co-starring Brian and the universe. And was also a finalist for the Pulitzer Prize in General Nonfiction. Brian is also an actual accomplished physicist. He's made contributions to physics. I can't describe them because I don't understand them, but that's what it says in Wikipedia. And he also co-founded with Tracy Day, the World Science Festival, which is here in New York. And the 10th was last year. When does the 11th?
I think it's May 29th.
May 29th. So right here in New York, World Science Festival. I want to say a little bit about how I first made contact with Brian by way of explaining kind of the context of this conversation. So I was brought to Union several years ago to do something different than what I'm doing here now, but that was on a Templeton Foundation grant, and the idea was that I would develop and articulate a worldview that qualified for the term spiritual, but was completely compatible with science. I kind of felt I had such a worldview. It was like pieces of it were floating around in books I had written, but I had never put it together. So one of the things I did is I gave 5 lectures at the end of this period that were meant to embody this worldview. And after one of the lectures, I looked at my Twitter feed, and somebody who had been there tweeted something to the effect of, I went to a talk by Robert Wright and found myself in the presence of greatness. Now, sadly, the greatness part was not a reference to me. Brian Greene was in the audience. And and that was the first I heard of it. I had actually taken a picture of the audience, and I looked at it. Oh, there's Brian Greene. I was very flattered. And then in the final lecture, I gave the lecture, we turned to Q&A, and a hand went up in the back, and oh, it's Brian Greene, challenging something I had said about electrons. Now, if you're going to be publicly challenged about something you've said about electrons, you'd rather it not be a world-famous physicist who's doing the challenging, but that was my fate. It was actually, it wasn't my description of electrons, but the way I characterized kind of the nature of scientific belief in them, and we may get into that. But in any event, if you're wondering what we're doing talking about physics at a theological seminary, it kind of gets back to these 5 lectures. In the first lecture, in trying to kind of define my worldview or set the stage for it, I cast myself kind of in contrast to the worldview of the so-called new atheists. And one of the things I accused them of was a certain amount of intellectual hubris. I mean, there have been these arguments made by prominent new atheists, arguments such as consciousness has been completely explained by science. I won't name names. But another argument was that science tells us all we need to know about values. Each of these was a book. Another was that science has answered the question of why there is something rather than nothing. And I thought the problem with these was not just that they overestimate the scope of science's domain and overestimate the mysteries that science has, in fact, solved, but I thought there was kind of a failure to appreciate the sense in which modern science is illuminating whole new mysteries. And I don't mean that in a trivial sense. I don't just mean that, when you answer one question, it leads to others. Like, once you know that DNA is the hereditary material, it leads to questions about how the information is encoded and transmitted. I think modern science is in some cases pointing to mysteries of kind of a different sort, mysteries that intersect with philosophy, with questions of meaning, and suggest in some cases that we may never solve them. They are mysteries that seem to point to the limits of the human mind as an instrument for grasping all of reality. And in that sense, I think that science in some ways is emphasizing how many possibilities are left open by science, possibilities of philosophical nature, even you might say a spiritual nature, you might even say in some cases a theological nature. So, and I think that there's, no single science that does more of this than physics. I think there are just a number of cases where you just go, this is imponderably weird. And so that's one reason I want to talk to Brian. He does not share all the beliefs I just expressed. We'll see how he comes out on some of these, but I think he's the perfect person for doing a kind of highlight reel of kind of modern physics, like mind-blowing things about modern physics, and pondering them with me because he's one of the more adventurous thinkers in physics, I think. So, with that as context, I want to start with a tweet. When you tweeted this event, we both, I guess, got a reply from someone who said, "Could the notion of particles be the greatest misnomer in the history of physics? It is a useful concept for the physicist, but gives the layperson an image of something like grains of sand. It obscures the reality that they are more like patterns in an infinite sea of energy." Is that fair?
I would say it's fair, except for the infinite sea of energy part at the end, and the most leading thing ever in the beginning. I'm not sure what's left, but
the particles. Is particles a misleading term?
So particle, it's misleading if you misinterpret it. So when we use it, we really do know what we mean. What we mean, however, does differ from the conventional English word that you'll find in the dictionary. So yes, particle, when you think of a grain of sand, that seems like a pretty resonant, that's a pretty good illustration of that idea. When we talk about particles, we have to invoke quantum physics. So that's really where the shift in thinking occurred. And the shift does cause us to think of a particle as an entity that is described not being at a definite location with a definite speed, which is sort of how you always think about a particulate ingredient in the real world. Instead, we think about it as an entity that has a certain likelihood to be at one location or another, and that likelihood is described by a probability field, and that probability field is completely unfamiliar. You won't find that in the dictionary under particle. And so we could fill out what that image looks like, but that's where the disparity is between English and our use of that term. So we never changed the word when quantum mechanics came along. We still use the historical term particle, but we have a very precise mathematical definition of what we mean by that.
Okay. So the idea is, as I understand, as you said, if you ask, in some cases at least, if you ask where is this electron right now, all we can say is it has like a 30% probability of being here, 30% here, 20 here, 20 here. And it isn't just that we don't know, it's that in a certain sense there is no answer at that moment. Now,
it depends on your interpretation of quantum mechanics, right. And here you come to the beauty of science. It's an ongoing exploration, and there are unresolved questions. You alluded to some at the outset, but even within science proper, within the field of quantum mechanics, there are very basic questions that we've yet to fully resolve. And the interpretation that you just gave, thinking about probability as not that we don't know, it just isn't at any location, not everybody will agree with that.
Right.
That's, I would say, the dominant perspective in the field.
Well,
but there's another perspective where the particle absolutely does have a definite position.
Well, Einstein believed that.
Einstein believed that, but he didn't actually have a mathematical theory behind it.
Right.
Since Einstein's time, there now is a mathematical theory. It's the dark horse of quantum mechanics. It's not the one that we teach our students, unless I'm teaching the course, right? I like to show them this other approach that doesn't get much airtime. It's called Bohmian mechanics. And it's a guy named David Bohm. Some people here may know of him. Also, Louis de Broglie was instrumental in thinking about these ideas in the 1920s. And I think for sociological reasons, not necessarily scientific reasons, that way of thinking about quantum mechanics never got the airing that it deserved.
So that's called the hidden variable model. The idea is, no, the particle, we can only say that it's 30% chance of here and here, but it's actually one of those places, and there's just some variable we don't know about, something in the universe that if we had the information about this thing, we'd be able to say for sure.
I would say it a little bit differently, but that's a fine description of it. But in the Bohmian approach, you don't even have to commit to the existence of a variable that would nail down its position if only you knew it. You simply come to the recognition that there are things that are definite in the world that yet are beyond your ability to ever access. And that's a curious state of affairs. It's one that's we're unused to. But
so it's a hidden variable we will never uncover.
That's right. In the traditional Bohmian approach, the fact that particles have definite positions but they're inaccessible to you is a natural part of the mathematical framework.
Okay. So that's slightly weird, but it's not as weird as most of the alternatives. I mean,
well, that's the point. If your barometer of truth is the level of weirdness, and if you say if theory X requires less weirdness than theory Y, and they're both compatible with the data, then let's go with theory X. And if that is the approach that you would take, I would say that the Bohmian approach is less weird than the traditional quantum mechanics that we find in the textbook. And the reason is, in the traditional approach, you have to give up the idea that there are definite predictions. You have to go probabilistic. But you also have to give up that things have a definite position and a definite speed. That's two things that you have to give up, that Isaac Newton would sit here and say, are you kidding me? That's the way reality is constructed. But in the Bohmian approach, you only have to really give up the idea that they're definite predictions. You can still have in your mind that particles occupy definite locations. So in that sense, it seems less weird than the standard approach.
Okay. So let's talk about, I mean, it's an interest, I mean, you're kind of paraphrasing Occam's razor in a sense, right? That's what you mean is the simplest theory should win and weird isn't simple?
Well, see, the problem with that is there are many different axes along which you can measure simplicity. And from a mathematical standpoint, some would say, well, hey, when you look at the equations of this Bohmian approach, it has this like other equation that lacks the simplicity of the equations that we're used to in quantum mechanics. It has a sort of nonlinear quality, if we allow ourselves to use the technical term. And people say, oh, because of that, it's more complicated. Let's put it aside. But the strange thing is, in the traditional approach, no one has answered the question, how do you go from the probabilistic haze that quantum theory describes the world mathematically to the definite reality of common experience?
Right.
And without bridging that gap, you've left out some kind of mathematics. So if you recognize that you've left out an equation, and you don't know how weird or complex that equation is going to be, it's difficult to use Occam's razor because you don't really have a way of judging the mathematical complexity of the full quantum mechanical formalism, since part of it, even today, is missing.
Okay. It's getting weirder earlier than I thought it was going to. So let's move to what are called some of the traditional interpretations, which are even weirder. I mean, there's one so-called interpretation that's not weirder because it just refuses to interpret. The Copenhagen interpretation kind of says...
That's the one I had in mind, by the way, when I'm saying it kind of refuses to commit
it's kind of, they kind of say, let's just don't think about the implications for reality. Let's just do the math. It's successfully predictive within certain constraints and so on. But then there's one that is taken seriously by a surprising number of people, surprising to me, which is the many worlds interpretation. I mean, we should say that, that one thing that is observed is that when you measure the electron, suddenly it is in a particular place. And this is kind of the mystery, the puzzle we're alluding to is that it seems to be the case that in some sense, there's this probability function at one point, but if you measure it, and if you accept the idea that the particle is in no particular place to begin with, then it is kind of snapping into definite existence at the point of measurement.
Yes.
And this has led to a couple of weird interpretations. Many worlds, I think, gets the trophy for weirdest, right? Do you want to talk about that?
Sure. So if the mathematics of a theory, which quantum theory, in fact, does do, says that, as you were articulating, say there's a 50% chance that the electron's here and a 50% chance that it's over there. And when you make the measurement, you say, find it over here. The puzzle is, what happened to the other possibility? And you might say, well, look, it just goes away, perhaps. In everyday life, when there's a chance of this or that and one outcome happens, you don't usually worry about what happened to the other possibility. You just think it wasn't realized. The problem is the math of quantum mechanics does not allow that to happen. So what do? Well, the most straightforward next step is to say, well, when you measured it over here, yes, you found it at that location, but the particle was actually also at the other location too. It's just in a separate reality, a separate universe. So you now imagine that when you make a measurement, in one universe you find it over here, and in another universe there's another copy of you that finds it over there. Each of you thinks that there's only one definite outcome. Each of you is only aware of one outcome of the experiment, but each of you would be wrong if you think that's the full spectrum of reality, because there are two of you, each having those thoughts, each measuring the particle at a different spot.
So in this view, I will myself branch off at some future point into multiple versions of me inhabiting multiple universes or multiple worlds and doing different things.
Yeah, the branching idea is okay in a context like this. It can get you into trouble if you take it too seriously.
I wasn't taking it seriously, don't worry.
Good. You can almost imagine that there sort of always are infinitely many of you, and they're just all going along in this way, and they're all having these distinct realities.
And, most people say this is crazy, but I want to emphasize that there's not that many clear alternatives to crazy here. And this is taken really seriously by some really smart people. In fact, some people say this is not an interpretation. Many worlds isn't an interpretation. It's what the theory literally says without us putting any interpretive spin on it, and we have to accept it.
Well, that's the amazing thing. However complex it may sound, however uneconomical it may feel to invoke this spectrum of realities, if you're just following the mathematical equations, this is the leanest possible interpretation of what the math is telling you. Right there in the most basic quantum mechanical equation, you see these distinct realities right there in the math. And a guy named Hugh Everett III in 1957 said, look, I want to find the leanest way of interpreting this theory. And he said, let me just put away all my prejudice about how reality is actually constructed. Let me not worry about things that sound weird. Let me follow the math. And this is where that trajectory does take you. Now you can say, so is that it? Are we done? And you're right. There are some people in the world today who say, absolutely, we're done. We've dotted the I's, we've crossed the T's. This is the way of thinking about the world. There are others, and I count myself in that group, who look at the arguments and feel unconvinced. And I can tell you why, if you're interested, why I'm unconvinced.
I can think of some reasons, but go ahead.
Yeah, so I'll just give you one. So, the basic way of thinking about probability is you should not be surprised if an outcome has a high probability and it happens, but your intuition tells you that the very meaning of probability is that if something has a very minuscule likelihood of happening, very small probability, if it takes place, there should be a degree of surprise associated with encountering that highly unlikely outcome, right? That's what probability means. But in the many worlds interpretation, when we say that every outcome happens, it just happens in a different reality, and there's a version of you measuring that outcome, well, that means there's 100% certainty that there's going to be a version of you that encounters every outcome and any outcome, however unlikely it may be. So how could you possibly be surprised if there's one of you encountering this unlikely outcome when you know from the outset that every outcome happens and there's a version of you that's going to encounter it? So that means you could never ever be surprised. If something has a small probability, with 100% certainty you're going to encounter it. And that seems to go right against the grain of what probability even means. Now there are answers to this. There's this group in Oxford, and they've developed a whole spectrum of mathematical ideas to answer this. The question is, do you find that convincing? And at the moment, I'm not convinced.
Okay. So there's another interpretation that I think is now a real minority interpretation, but it's been taken seriously by really smart physicists. I think Leo Szilard may have been one. I'm not sure. But the idea is that, I mean, they looked at this fact that measurement seems to bring the thing into definite existence. And they speculated that maybe it's the person observing the measurement, in a sense, it's consciousness encountering reality that brings it into definite existence. I think that's a real minority view now, but again, it's an illustration of how hard it is to
Yeah, I mean, it is a minority view, because I think most physicists are uncomfortable talking about consciousness, in that we don't have a mathematical articulation of what it means, and therefore we feel at sea using words that we can't back up with equations. But it's very hard to refute that possibility, because anything that we are aware of, we are consciously aware of. Therefore, our consciousness is part and parcel of any single observation or measurement. Mm-hmm. And therefore, how can you ever say that your consciousness wasn't part of what brought that reality that you are now aware of consciously into existence? You know, the traditional response is, hey, so I mean, Einstein's response would be, so wait, so if my consciousness can cause the spectrum of possibilities to ante up and become a definite reality, is it because I have a PhD? Could a mouse have done it? Could a computer do it? Could a photon from the microwave background radiation banging into a particle, would that be enough of an observation to cause it to have a definite reality upon that interaction? And it seems like the answer to all these questions is yes. It doesn't seem that consciousness needs to be injected into those processes, but for us to check whether that photon bouncing into the particle gave it a definite reality, we'd have to be involved, and therefore consciousness would be mixed into the soup. So it's very hard to ever refute that idea fully.
So it's pretty unfalsifiable.
It seems
in principle.
so, yeah.
Okay, so one implication of the most common interpretation of, or set of interpretations of quantum physics, that is to say the non-Einsteinian, the non-hidden variable, is that things happen in this universe for which there is no cause in this universe. In other words, truly random things. I mean, when we flip a coin, we think, well, you can't predict whether it's heads or tails, but the reason is there if you knew everything about the wind and so on. But according to quantum physics, when a particle is going to turn out to be heads or tails, so to speak, whether it is one or the other has no cause in the physical universe.
In the quantum version.
Yeah. We're in the mainstream view of quantum physics today, which is itself very strange.
Right.
Which sounds like not a scientific worldview, in a sense.
Well, I wouldn't go that far. I would say that it's at odds with the historical scientific worldview that we're all used to, and the one that Isaac Newton laid down. And it's shocking that that view is being challenged. But to say that a perspective is non-scientific, to my mind, would be to say that it's incompatible with being tested observationally or experimentally. And here's a theory which is not only capable of being tested experimentally, it's the most precisely confirmed theory in the history of the species. You make predictions about the magnetic moment of the electron, and you can calculate it with quantum mechanics to 10 decimal places. And then you can go measure it in the laboratory, and digit by digit by digit by digit, right down the line, there's complete agreement. So if one's going to call that a non-scientific theory, I don't know what science is.
Yeah, I just mean it runs against what the average person thinks of as a scientific. The average person thinks of a scientific worldview as saying there's nothing we can't explain in principle. And here we see things happening that have no cause in the physical universe.
That's right.
Now, when in a previous conversation, I got you to take seriously a kind of a scenario involving this that is, you know, I don't want you to take it too seriously. It's just for purposes of thought experiment and to suggest, you know, how far you could go with some of these things in principle. And the idea was that if you were running the universe, I mean, if you were God, so to speak, and you wanted to influence events, you could do so within the constraints of this worldview in the following sense. I mean, the constraint is that the number of heads and tails, so to speak, have to be 50-50 in the end. Or let's look at it as a roulette wheel. The constraint you're working under is that that once every 36 times it lands on number 7 or on number 36. So the odds have to even out in the long run. But if you can put a magnet or something under that roulette wheel secretly, you can determine who wins and who loses within the constraints of the overall probability. So does that make sense to people? So it still looks to the casual observer that, well, when every 36 times it lands here, it's half the time it's red, half the time it's black. There's nobody fooling around, but there is somebody fooling around. They're deciding when it's red and when it's black, and that's very consequential. So in theory, you could have, you know, I mean, I don't want to use the term divine intervention in this setting, but and it is just like a thought experiment, but it's the kind of thing that's not ruled out.
True, but I suspect, and I won't weigh in on it necessarily, but that feels like an incredibly impoverished version.
Oh yeah.
Of divine intervention. That God is doing the calculations that Niels Bohr told him to do. Right, and he's looking up this probability table, and then he's making sure that the magnet, oh yeah, okay, I can put it here now. What does Niels say? Oh yeah, I can put it here. It just feels like a pretty weak version of a deity.
Yeah, although in this scenario, he set up the things that Niels Bohr discovered. But I mean, it would explain, you know.
But once he does that, then I don't see the value of introducing him or her or it back in the back door, because that all-powerful presence would have been able to not be too disturbed by events in our world that lack the kind of prequel that you're looking for based on your Newtonian intuition.
But it would explain why all these football players after the Super Bowl say, God was on my side, and that's why we won, right? That's important data that needs explaining. It is important data.
I have other theories about that. But,
No, I mean, I want to emphasize that this wouldn't even be taken seriously in most modern, you might say, liberal schools of theology. I don't mean liberal in the political sense, but liberal in the sense of modern theology. And by the way, Union was kind of the epicenter of that in the 20th century, and you know, people like Paul Tillich were here, and so on. So that's not it's not like that's the conception of God prevailing in modern theological circles, but it's.
But I agree, it's not incompatible.
Well, and it's testament to just how kind of weird the whole thing is.
Right.
So another weird thing is quantum entanglement, where just, you know. So again, there's two particles. They can be heads, they can be tails. They can be very far apart. You measure one, it's heads, and that instantaneously determines what the other one is going to be. I think you might say it's tails usually because they're complementarity, but whatever. The point is,
you can set up any way that you want.
The point is, influence is moving instantaneously, and this was something that Einstein thought was not possible. He recognized this as an implication of quantum physics. He says, this is why I think they're wrong about something. This couldn't be the case. But now we're pretty sure it's the case, right?
Yes. So 1935, Einstein, with two colleagues, Podolsky and Rosen, recognizes this weird quality of quantum mechanics and is quite excited about it. Because while he wrote the second paper on quantum mechanics, and the subject really owes, historically, Einstein an incredible debt of gratitude, he didn't like where the theory went. So he was happy when he came upon a feature of the theory that he thought if he presented it to the quantum mechanicians, they would agree that there's something wrong or something else that's necessary. And it was exactly the issue that you're talking about. You have a particle over here in New York, another particle over here in California. You set it up in such a way so that measurement on one seems to have this instantaneous effect. I put that in air quotes because it's a very specific quantum mechanical effect, but it seems to have some sort of effect on a particle that's very far away, and as you say, instantaneously. And that's much faster than the speed of light. So Einstein, in that paper with Podolsky and Rosen, offered what he believed was the road toward a solution. And the road toward a solution was to recognize that the probabilities that quantum mechanics was giving us, and when it says that there's a 50% chance that particle is here and 50% chance that it's here, Einstein said that's simply because quantum mechanics is a very weak theory. It's not a very good theory. There's a deeper underlying theory that we have yet to find, and if you had that theory, it would tell you that the particle is definitely there or definitely there. So there's no notion of probabilities, there's no notion of things being in an undefined state. And when you inject that into this entanglement picture, you find that the puzzles, in principle, would go away. Mm-hmm. The problem is that theory gives rise to, not the problem, actually the beauty, that theory gives rise to predictions that even Einstein didn't realize. It took the genius of somebody else named John Bell in 1964 to re-examine Einstein's work and say, wait, if Einstein's right, we can actually test that in the laboratory. And it took until the 1980s, but when this idea that particles always have definite characteristics, even if you don't know them, when he tested that in the laboratory, it turned out that it seemed to violate Einstein's way of thinking about things. So what does that mean? Well, the arguments are quite subtle, but many of us believe that what it means is that it doesn't necessarily rule out that particles have these definite qualities, but it seems to require that the world is non-local. Mm-hmm. It seems to require exactly the thing that goes against our intuition, that what happens over here really can affect what happens over there. And that's not what we're used to, right? You know, I push this over here, I think you'd all think it was some sort of magic trick if I pushed this over here and that cup started to move in tandem, right? But according to these quantum mechanical ideas, in a very subtle and mathematically precise way, what you do here has an effect over there.
Mm-hmm. I mean, I guess you can see why Einstein wouldn't like this. I mean, I gather one of the achievements of relativity was that you no longer had to think of gravity as being this thing that, you know, kind of spooky action at a distance. These two things pulling on each other, it could be described, we probably don't have time to get into details, but in terms of just local effects, as something rolling along the fabric of space-time as it has been warped by a heavy object or something. So he had gotten rid of that weird kind of action at a distance only to run into this. And this is now taken seriously. And do physicists do they wake up at night and go, no, this is too weird? I mean, is it just...
Well, it's taken so seriously. I mean, you know, the progression of changes of paradigms, right? At first, you know, some new idea is put forward, everybody says it's impossible, right? Then, assuming it's right, a little while later, people warm to the idea and integrate it into their thinking and start to think, yes, that's how the world works. And then, you know, 5-10 years later, it's like second nature. And you're like, yeah, of course that's how it is. So right now, entanglement from the standpoint of physics is that. It's just, yes, that's just how the world is. And people actually make use of it. It's no longer some abstract idea, some strange feature that might be an esoteric mathematical quality. We have entanglement being used between, you know, Chinese satellites and laboratories on the ground, allowing them to have this weird spooky connection in the most flat-footed, straightforward, applied manner.
But I assume there's a reason this doesn't lead to like woo type things, right?
Yes, it does. and the reason for that is the nature of the connection is such that there's no data, there's no information that's literally being transmitted from one particle to another. Rather, the connection is so subtle, it's so ephemeral, that it's better thought of as a long-distance correlation that's locked in by the laws of quantum physics.
But it's not locked in the sense that, like, these two things are spinning at the same rate when they were together and then they get separated, so the correlation remains. The correlation, in a certain sense, does not exist until they're well apart and one is measured as a real thing.
It depends exactly what you mean by that. I mean, you could measure at any point. You can measure when you're nearby, and the same thing would happen.
Sure.
But yes, I mean, the canonical version of this is you have a particle that can spin like a top.
Right.
And it can spin clockwise or counterclockwise, which we typically call spinning up or spinning down. And a particle, because of the weirdness of quantum physics, can be in a mixture of up and down at the same time.
Right.
And only when you measure it does it snap out, either up or down. That's the usual weirdness of quantum mechanics. The entanglement weirdness is now you got these two particles that are both in a fuzzy mixture of up and down at the same time, right? And you measure the one in New York and it snaps up, and the other one snaps out of the probabilistic haze in California and spins down. And that's the strangeness. But notice that it does require that these particles are in this sort of fuzzy...
They're in the haze, and that's the sense in which the correlation doesn't really exist until the moment of measurement.
In a sense, yes.
So... But you can't, as I think you suggested, you can't use this to actually transmit information instantaneously, because you can't, like, yourself decide this is going to be heads and say, hey, if you see tails, it means this. You know, the particle decides itself, so to speak, what state to assume. So we cannot encode information.
Yeah, so I mean, the weirdness only becomes apparent when you take your data over here in New York, and let's say you measured the coin, you got heads, tails, heads, heads, tails. And then I did my measurement independently of you in California, and I got my list. We bring them together and we find, wow, every time you got a head, I got a tail. Every time I got a head, you got a tail. And that's where the weirdness comes into play. But it's still a random assortment of heads and tails, and therefore there's no information that we can extract from that.
So speaking of Einstein, he in the Einsteinian universe, I guess, and I think this is a part of his thought that more or less holds up, whereas you tell me, but I mean, hidden variable is now held in some doubt. But I think the idea of the kind of block universe or block time, where time is just a dimension, just kind of like spatial dimensions, more than we realize. So one implication of that, you know, it's I guess, correct me if I'm wrong, it's a kind of deterministic notion in the sense that as we move forward in time, it's very much like just moving north in space, in the sense that whatever you see as you move north was inevitable. It was there. Whatever you head in direction of Chicago, you're going to see Chicago. It was there. It was inevitable. And in Einstein's universe, time is kind of the same way. You can't see it yet because you're only moving 1 second per second, you know, but it was inevitable. And now that's a I mean, first thing to say is that seems a little at odds with the kind of indeterminacy of quantum physics, but I gather that's not a true deep contradiction, because mainstream quantum physicists would buy into Einstein's universe?
Well, the vocabulary that you need to use to describe a classical deterministic world, which is, I think, what you have in mind, a Newtonian or an Einsteinian version, the vocabulary is a little bit different from the quantum mechanical one, but when the dust settles, they're, for all intents and purposes, pretty much the same, which is that the equations governing physics are deterministic. That is, you tell me how things begin, and I will then use the laws of physics to predict the state of the universe at any future time. And nowhere in there is there room for you to step in with free will, or for there to be something that stands outside the mechanistic, deterministic, turn the crank mathematics that takes you from here to there. Now, the footnote is, what does it mean, the state of the universe? In an Einsteinian world, it's telling you literally how things are. In a quantum mechanical universe, it's telling you the likelihood that they're one way or another. But those likelihoods are still rigidly determined by the quantum mechanical laws. So there's no room for anything else in this description of reality.
And if moving forward in time is like just walking along north or south, then in principle moving backward in time, I mean, you hear this, that there's no reason, according to physics, to think you can't move in principle, backward in time.
Yeah, I mean, the laws are completely agnostic on what's forward in time and what's backward in time. They don't care. So if you turn the crank one way, the laws will take the state of the universe and evolve it toward what we conventionally call the future. But if you turn the crank the other way, and any reasonable high school student could do this with the equations, the laws will take you from the state of the universe now to the state of the universe in what we conventionally call the past.
Right. I know someone, you actually may have heard of this person, person, some accomplishment, who actually I think that he has been contacted by time travelers. For obvious reasons, I will not mention the person's name. Is that... I'd love to be able to go say, Brian Greene says this is totally possible. Would you?
Is this person like in a locked ward?
No. It's just,
Well, you see, that's part of the problem. I mean,
that
even
the
if
person's not in a locked ward, you mean?
Yeah, well, you can say, where are all these people from the future if you could go back in this way? And, we know what we do with them.
I think they communicate subtly in this scenario.
It's one thing to say that the laws of physics are compatible with a sequence of events going forward in time or that sequence of events going in reverse in time. It's very hard, however, to execute these journeys. And when the journey is toward the future, time travel, if you want to say toward the future, we know exactly how to do it. You give me an arbitrary duration of time that you want to jump ahead on planet Earth, and I'll sketch out exactly what you need to do it. For the reverse, if you say I want to go back a certain number of years, there are a number of conditions that I will require of you to have even a chance of being able to do that. And it will be difficult, perhaps even impossible for you to meet those requirements. As of today, however, there are viable time travel to the past scenarios that have yet to be fully ruled out. But I think most of us believe that when physics matures, at some point we will be able to rule those out, and therefore time travel to the past won't be possible.
So did you see the movie Interstellar?
I did, yes.
How did that look from a...
Well, I didn't understand it.
Well, there were...
there was
that
I know
problem.
I know there's a book. Kip Thorne, Nobel laureate, wrote a book on it. I've not read the book. But, if it takes 300 pages to explain a movie... Like, when I go to a movie, I just sort of want to take it in. But I enjoyed it. And there were real scientific moments in there, so don't take that the wrong way. The visualizations of black holes were the most precise visualizations that we have ever had. They were generated by the fundamental equations, so that's amazing. And also this notion of time slowing down near the edge of a black hole, which was a plot device there, that also is something that we fully understand from Einstein's general theory of relativity. When I say I didn't understand the end. But that's okay.
Yeah, I'm trying to remember. Yeah. There was one true paradox in the plot, but that tends to happen with time travel scenarios famously.
Was there time travel to the past? No, it was only to the future. Yes, I think it was only to the future. I'm just going back a little bit. Anybody? Yeah, it was, right? Yeah.
But then they went back, right?
Did they go back?
They communicated.
They communicated back. Okay.
Yeah, they were sending signals.
Maybe that's what I missed.
They were sending signals through the bookcase or something. Quickly, this is actually not in your domain so much because it's more cosmology, but there is this, since you mentioned black holes and we're talking about weird things, there's this Lees-Mullen idea that black holes may be the way universes replicate, and, if you accept that, it could be the case that universes themselves are subject to a kind of natural selection in that those universes most conducive that have the properties that are most conducive to replication are the kinds of universes that come to dominate, just as the most fit animals come to dominate. And maybe that's why there are so many black holes. And then there's a further variant of this, according to which intelligent life facilitates the replication of universes, which leads to universes in which life forms and evolves for intelligence. That's just a footnote, unless you want to say anything about it.
Natural selection is one of the most powerful ideas that have ever been put forward. And the beauty of natural selection is it's almost a tautology, right? It's one of those wonderful ideas where you can't even imagine how it could not be correct.
Right.
And so it's natural then to take that idea and expand the domain in which it has been applied. And people have done that to a remarkable effect, right? So there's natural selection even at the level of molecules that may have been a precursor to the formation of life. Lee's idea takes it to a pretty extreme application. It makes, in principle, predictions that our universe should be among those in which the kinds of black holes that we have are the most fecund. They are the ones that will generate the greatest number of progeny by a process that you alluded to. The problem is it's hard to exactly see what that process is. It's hard to nail this down. And I think if Lee were here, we'd say it's still a viable approach, and perhaps it is. So it's an exciting idea, but I think it's one that is pretty far beyond what anybody now takes as mainstream.
And I should say something Lee would say if he were here, which is that second variant I mentioned is not one the one where life is a prerequisite for the replication of the universe is intelligent life is a prerequisite for the replication of the universe. That's not so much his. He acknowledges, yeah, it could be the case, but there are other people who kind of put that forth. I like that scenario just because it illustrates the sense in which, in principle, life could have a, quote, purpose, but it was not infused by some deity in the traditional sense. It was just infused by a process, much the way organisms are infused with goals, like to reproduce, to eat food, and so on, by the process of natural selection. So I have kind of a special fascination.
But I would encourage you to give up this idea that life has to have a purpose.
It doesn't have to. It doesn't have to.
But I would even say give up the idea that even if that theory is true, that is the purpose of life. I'd say that's the mechanistic role of life in this particular way that reality is constructed. And I think it's more noble to find your own purpose and not look to some quality of the universe to bestow purpose upon you.
Okay, so wait, so there's two things,
one person agreed with me,
no,
which I
two
really do
people
appreciate.
agreed with you. This reminds me of the time I debated Sam Harris. Are you Sam Harris fans? Two people have clapped? No? Okay, good. You can stay. I'm afraid you'll have to leave. Two things. So you're saying purpose isn't the right word. You can argue. I mean, in a way, you should be. Well, anyway, some philosophers use purpose in this way, like Dan Dennett, speaking to atheists, says life. You can speak of organisms as having purposes. They're just imbued by natural selection. No God, no nothing, and I think it's a long and separate argument whether. There's reason to believe that natural selection evinces hallmarks of purpose, that there could be a purpose unfolding on Earth through nature. I've actually argued that there is evidence, but I want to emphasize, I'm just talking about natural, plain old nuts and bolts mechanistic natural selection, nothing spooky. And the point is just that if it's the case, that doesn't mean you should like this part. It doesn't mean there's a God. Could be that it's more like a process of natural selection that imbued the purpose. And in that case, I would certainly not say we should do what you don't want done, which is derive your meaning from that. I mean, I wouldn't say that organisms, that the purposes instilled by natural selection are noble. At all.
No, it depends on how you use the word purpose, and I was using it. I thought you were referring to the more traditional sense. But by the way, just as a small footnote to your footnote, I got nothing against God. By the way.
Oh,
so,
good.
So don't point to me and say, "Hey, you like this because you got no God."
I hear that he speaks highly of you too.
Yeah. Well, that's very nice.
Anything else you want to say about that? I mean, you're finishing a book that gets into some meaning of life-y territory, right?
Yeah, sort of, yeah.
Sounds like you're being a little coy here. Sounds like there's nothing else you want to say about this book right now.
Yeah, not right now, but yeah.
Nothing else about God.
I'm happy to talk about whatever you'd like to talk about. I'm so easy.
Okay, well, talk about God. No, I have no questions. I just want to hear you talk about God.
Yeah, it's a little hard to do it that way. But does anybody have a question on God?
Wait, we are about to turn to questions, but I want to, in about 5 minutes, but I want to, let's see if there's anything else. Well, let's get back to the question that was implicit in the way I started this with, like, well, what is an electron, really? Which is kind of, is materialism an apt description of the modern worldview of physics? I mean, scientific materialism is kind of the famous phrase associated with science. Some people find it a depressing phrase. In some cases, that's because they associate it with determinism, maybe, which isn't entirely apt in light of quantum physics, maybe. But in any event, you know, it's the idea is some people find it dispiriting to think that everything is just this like physical stuff. There's nothing more ethereal or spookier or whatever. And I do, without signing on to what their aspirations are, I do think the progress of science has tended to make us skeptical of the idea that there's really stuff at the bottom you can kind of grab, right? I mean, because it's like, okay, these molecules, that's what it is. Well, molecules are made of atoms. Okay. Well, it turns out atoms are made of these protons and neutrons. It turns out they're made of something else. And it turns out, when you describe particles, actually, they're in a fuzzy haze. So what would you say is the status of the word materialism right now?
Well, I'd say it's alive and well, but you have to allow yourself to update it based upon discovery. So I agree that the rock bottom ingredients, like the fundamental furniture of physics, is somewhat hazier than it was in the time of Newton, right? I mean, Newton, it was the stuff that you could touch. It was just like smaller versions of it, right? That's what the ingredients would be. Whereas now we do have to, as we started the conversation, graduate to a picture where the particles have this more ethereal, fuzzy quality. But at the same time, you can set up equipment where a little dot on that equipment was formed by a photon or an electron impinging on the material. So in a concrete sense, you can measure the electric charge of the electron and get a number. You can measure the mass of the electron and get a number. You can fire beams of electrons and predict what they're going to do when they slam into various targets. So it is the case that you can't clutch it in the same way that you can clutch tables and chairs, but you can clutch it with the mathematical equations with an even greater precision than you could have using the Newtonian mathematics. And in that way, if you allow your clutching of the fundamental ingredients to invoke the equations of physics, we've got it fully in our grip.
Yeah, it's better than Newtonian in a sense, maybe, or more precise, whatever the word uses.
Yeah, that's what I mean, just that.
But it is only probabilistically predictive, unlike Newtonian physics.
But get over it. I mean, that's how
Yeah,
the
but
world
I mean,
is.
but some people would call that, in some sense, a shortcoming. I mean, a degree of finiteness has been lost. A degree of precision, a degree of certainty has been lost.
Well, I would say that the Newtonian picture of what constitutes reality needed to be updated. It was a flawed picture. It was a nice picture. Right. It made us feel good. We could really wrap our heads around what reality is. It's just what you see, scaled down. But when you scale down, it turns out it's not just what you see. You have to introduce new ideas, new concepts, new language. But the fact that we've been able to find the language and articulate it mathematically and make predictions that, as I mentioned, agree to observations in 10 decimal places makes you feel pretty good. Makes you feel like you're on the right track. Makes you feel like, yes, there is some significant amount of truth in what you're writing down.
I mean, the Newtonian picture just breaks down at a certain level.
And is replaced by one that's spectacularly precise. So if your notion of, to go back to your question, materialism invokes these new concepts and the new mathematics, then yes, as far as we know, that is the rock bottom structure of reality.
But I guess if somebody, well, let's turn to you're an advocate of string theory.
I wouldn't say I'm an advocate of string theory. I work on string theory, and I'm an advocate of things that are borne out by observation and experiment, which has not yet happened for string theory. Okay. So, and I don't mean to parse words here, but I find that I'm often described that way because I happen to write a book on the subject, and I go around and I talk excitedly about the possibilities of the subject. But advocacy doesn't really have a strong place when you're talking about cutting-edge ideas. observation and experiment is the only barometer that you can use, and we don't have that at our disposal yet.
Okay. I withdraw the term advocate.
Okay, thank you.
In any event, the idea is...
Especially with John Horgan sitting in the front row. But anyway.
Oh, look, famous science writer John Horgan, just waiting to pounce. Not quite yet. So on this string theory thing, so the idea is that that what we think of as different particles, actually, no, they're not different particles. And maybe this is a little metaphorical, and you'll tell me if I get it wrong, but actually, no, there's just one kind of string. I guess they're in circles, but in any event, one kind of a string, and they vibrate at different frequencies, and that's what we take to be particles. One frequency of vibration means one kind of particle, one frequency means another kind. So I guess certainly, if that's the right metaphor, then yeah, the particle thing kind of breaks down, seems to a layperson. But in any event, if somebody says to you, what are the strings made of? Yeah. It's not real string. What is the answer?
Yeah, so I get that question, obviously, and I get it frequently. And the answer that I give is that there are two possible responses. It could be that if string theory truly pans out and is the fundamental rock-bottom description, that the notion of what the strings are made of would be a kind of question that doesn't actually make a lot of sense. Because there are things in the world that we're very familiar with, and most things, I should say, are made of something else, right? But if you're right down at the rock bottom, fundamental ingredients, the notion of what they're made of is where that question ceases to have meaning. And a metaphor is not a bad one to use in this. You know, if you take a book, right? A book has got pages. The pages on them have printed paragraphs. Paragraphs are made of sentences. The sentences are made of words. The words are made of letters. But from a phonetic, what is a letter made of? I don't know. What's a letter made out of, right? It's a place where the question seems to not really have the import and impact that it does at the higher level of structure. And that may be the case with strings. But the second answer is we don't know if the theory's right. We don't know if it's even relevant. And that being the case, it could be that if it is relevant, maybe it's a stepping stone. Maybe it was molecules to atoms, to subatomic particles, to strings, to something else.
Right.
And there are ideas of what the something else potentially could be within the mathematics of the theory. The description you gave is a good one, but it's a description that could have been given, and I still give that, by the way, so I'm not criticizing you, but it's a description that really could have been given in the 1980s. And since the 1980s till today, there's been a lot of developments, harder to describe, but they do flesh out the picture with other ingredients and other ideas.
Yeah. Well, I guess you could ask the question of a non-string theorist. You could certainly say to the quantum physicist, what's this fuzzy wave made of, right? And you tell me, I mean, is it made of information? That's a probability distribution is information.
Right. Well, some physicists would say the wave is a mathematical device. It's not real.
Right.
So don't take it so seriously. It's just our equations that allow us to make these predictions. So don't ask me what it's made of, because it's not part of the real world in the same sense that tables and chairs are part of the real world. Others, however, will say this probability distribution is a real thing. It truly is a distribution, a field out there in the world, like the electromagnetic field or like the nuclear force fields. And to ask what it's made of conceivably would be a relevant question. There's not much that can be said about it, but if it's real, you can ask that question. Whether it's applicable in the sense that there's a sensible answer, I don't know.
Yeah. Now, there are physicists who say, certainly people who say, well, at rock bottom, it's information. That's what it is. And I think you have problems with that.
Of course, many of my close friends are among those. And it's hard for me to see how that really works. To me, information needs to be instantiated in something. It needs to be carried by something. It's hard for me to see that at rock bottom it's just the information, and somehow that entails the existence of entities that will carry the information. I don't see that link.
Right. So your point is, I mean, what we call information, like print on a page, has the material instantiation.
Yeah.
You can't say that's just information. It's actually molecules of ink on physical paper. So the kind of information we are familiar with is not foundational. It exists on top of a foundation. And And I don't know what the people you're talking to would say in response to that.
Yeah.
I guess they have something. I mean, another interesting thing about information is the kind of information we communicate, put on newspaper, you know, the sound waves of my speech it's in a certain sense an incarnation of, well, I don't want to get too weird, but an incarnation of human consciousness, in a sense. I mean, it emanates from human minds. And so maybe they mean a little, you know, I mean, maybe I shall close with a theological flourish. I mean, I mentioned that Paul Tillich was here at Union, and he famously defined God as the ground of being, and was famously criticized because that sounded like, you know, just, you know, meaninglessly abstract or something. But I guess maybe you could imagine that the information at the foundation of things is an emanation of something like a mind.
Yes, and I can give a concrete, I don't mean to undercut your theological
Feel
flourish,
free.
but you know, there's a very flat-footed version of that, which I think we've discussed at some point, which is the possibility that we're all living in a simulation, right? Now, I don't take that idea really seriously, but the reason I find it interesting is if we are in a computer simulation in some teenager's garage, you know, and, you know, 10,000 years into what we would call the future, then yes, we would all have emerged from that teenager's computer simulation who presumably programmed it, so you could say we are the manifestation of the teenager's mind. And that's fine with me because there's nothing that stands outside physical law. That teenager is subject to the laws that apply to the external reality, which maybe they're the ones that we know about. If that teenager has programmed those laws into our world, maybe they're completely different. So there's a version of that story where you don't need to use any traditional notion of God or divine being. You just allow for this possibility that minds are sufficiently powerful to create worlds in which there are beings that consider themselves sentient, that have some conscious awareness. And if that's possible, we don't know if it is, but the future will show it to us one way or another, and the vector, in my opinion, seems to be pointing squarely in that direction, then we will have conscious beings who wonder where they came from, and they may have come from other conscious beings.
That we will create things complex enough to have consciousness.
Or if that teenager programs us with the capacity to program that computer within the simulation, then that's what will be going on. So,
well, if this was all created by a teenager in a garage, that would explain a lot, I got to say. But, I mean, the other thing I'd say...
Well, you know, the theory is that, you know, in the, that all things were going well, and then the teenager handed the controls to his dad in November of 2016.
Yeah.
And Dad was a little, you know, they got the thumbs going on there.
Yeah. I mean, the thing, but the thing about that is, you know, you said, I'm not sure how much practical difference there is. I mean, that is a theological scenario, right? And
I agree.
Yeah.
And in fact, you know, I've had people write to me, you know, this is not my idea. It comes from various people, Nick Bostrom in Oxford, so I don't want to take credit for it. But I have people write to me about articles I've written about this, and they say, that's the first time in my life when I'm willing to accept something that feels theological, feels like a God. Because there is a creator, but the creator is not standing outside of a body of physical law.
Right. It's a naturalistic God. So, I promised we'd turn to questions. And so, if people have questions, put your hand up, and we hope that someone will appear with a microphone.
This message is question is for Brian Greene. I was wondering if quantum computers turn out to be real, like all the scientists agree that they all work, and there's no like debate as to whether one has more qubits that are working or not working. That, along with like the double slit experiment, do you think that would be strong enough evidence to say that the many worlds interpretation is correct? So you have the quantum computers working, and they're trying to factorize large numbers, that there's not enough space in this universe to factorize, so that means that they must be factorizing them in other universes. Do you think that if that turns out to be true, that would be strong enough evidence to say possibly the many worlds interpretation is correct?
Yeah, so it's sort of a famous argument that goes back to people like David Deutsch, who is one of the strongest proponents of the many worlds interpretation, who has made statements akin to that. I can't say that I am convinced by those statements. Quantum computers are governed by a quantum mechanical process, and the quantum mechanical equations are the same ones that a many worlds person would use. And we would go through the same chain of mathematical deduction to understand what they're doing and how they're functioning. And it's hard for me to see where somehow in that process I'll be boxed into a many worlds interpretation. The equations are the equations, and I'll follow them with the mindset that feels right based on the interpretation that I use. So I am not one of the people who claim that once we have quantum computers of a sufficient power, we are done with all the puzzles of interpreting quantum mechanics.
But conceptually, is the idea behind some kinds of quantum mechanics that you're actually getting the different versions of the electron to calculate simultaneously?
Yes, that's the popular description that one would give of a quantum computer is to say, hey, let's harness all these different worlds in order to do a calculation much more quickly than we could in a single universe. Have all these calculations happening through physical processes taking place in these parallel worlds, and then somehow pick out the answer that we're looking for from one of those worlds, and in that way we've done something that we could never do in a single world. But everything that I just said, it does have a translation in a more prosaic, depending on your metric, version of the quantum mechanical story. So I don't see it.
Brian, what keeps you up at night?
Well, I actually have been unable to sleep the last few weeks. I'm wondering if somehow you're aware of that. Maybe you can tell me.
Time traveler.
But talking more poetically, the questions that really drive me strongly, and that I hope that maybe we'll have some insight into before I pass on to some other realm. Where does time come from? I think that to me is the big one. Somehow space has got its own weirdness to it, but time somehow, maybe because it's so intrinsic to how we live a life, it's in some sense the most precious commodity that any of us ever has. And yet, even though we know so much about the nature of time, from Einstein's special relativity, Einstein's general theory of relativity, some work that's now being done even in string theory and quantum mechanics is talking about weirdnesses of space and time as well. But is time fundamental? Is it something that we impose on the external world in order to organize perception in a way that allows us to exist? Or is it something else? Could it be that time, like this table, is made up of more elementary ingredients? Could there be atoms or molecules of space and time that can exist and yet only yield familiar time when they choreograph themselves in the right way? How amazing would that be to sort of have an atom of time? Does that make any sense? Those are the kinds of questions.
But if Einstein is right and time is in a pretty fundamental sense very much like spatial dimensions, I think I asked you this once. Isn't the weirdness of time just an artifact of the way our minds happen to work? In other words, can you imagine animals, I don't know if animals would be the term, but beings with different a priori assumptions built into their brains, and to them, it's like time, yeah. I look back, I see the future, I see the present. It's this north-south thing that's weird. I just can't tell what north is going to bring tomorrow, right?
Sure. Q, right? There are. We have imagined. Science fiction writers have imagined such beings. It's hard for me to think about what would be required in the conscious experience of such a being to have that as their true perspective on space and time. But yes, in some way that I don't understand, if I could sit here and see the full expanse of time, I just sort of do this and see the full expanse of time, and somehow I can't do that for space. Of course, the puzzles would be isomorphic and interchanged. But it's hard for me, with my understanding of how reality is constructed, to imagine how that's possible.
I share your intuition that time is weirder than space.
From a layman's point of view, I'm trying to understand the nexus between science and spirituality. And Brian had mentioned when it got to the issue of consciousness, he kind of like, whoa, I don't go there. And you also had mentioned, Brian, that in the equation, sometimes there's a part of an equation that's missing. So my question is for both of you. What is consciousness? Why is it such a problem? Is it at the border? Is it the nexus between where the two of you are sitting? Is that the nut that is? I'm a layman. I'm
Yes.
just trying to understand consciousness.
Yes, can I give one and then you? I mean, so I think the caveat that probably should be said at the outset is nobody has any idea what the real answer to your question is. So let's place that as at the starting point. But researchers have made progress in ways that I think shed light on the puzzle, at least. And to my mind, it seems as though recent work suggests that consciousness may be less mysterious than our intuition leads us to believe. It is very odd that right now I have this little voice chattering inside my head. It's very odd that when I can't sleep at night, I can't get that voice to shut off. It's even stranger when there are multiple voices in there, but I'll leave that for my discussion with my therapist. So the question is, what is that, right? And that was a joke, by the way. I see a couple people looking at me like, not that there's anything wrong with having, now I'm in a very strange way. Can you shut the camera off right now? I'd appreciate that. So the question is, what is that? What is that? And there's work that suggests that what we are as beings that have survived, part of how we survive via natural selection is we've been able to form various models of what happens out in the world, quick and dirty models that allow us to size up the environment so that we can survive, right? I look around and I quickly size up the floor is solid. I feel like I can walk over there. Very, very basic intuitions and judgments about how the world is constructed. Now, we also have models of other beings. And Dan Dennett came with a term called the intentional stance. Other people call it theory of mind. When I look out and I see a living being, I tend to ascribe it agency. I tend to ascribe it consciousness. I look at you and I pretty much assume that what's going on inside your head structurally is pretty much what's going on inside of my head. And that's a pretty good assumption to make because it helps us to survive, right? If we make a mistake and I ascribe agency to the piano, big deal. It's a little silly for me to imagine the piano is thinking. But if I fail to ascribe agency to a snake out there on the savannah and it comes and bites me, I can die. So the brain tends to place agency all over the environment. Now, those models of agency out there in the world, we also apply it to ourselves, right? So I would describe consciousness as my being aware that I'm aware. And that awareness of my own awareness is itself a model. It's an incomplete model. It's a model that leaves out a whole rash of underlying details. And because of that, it feels like my sense of self is floating in this ethereal space between my ears. But that would be an artifact of an incomplete model that has allowed us to survive. I don't consider that to be the be-all and end-all of what consciousness is. But for me personally, it casts it in a light where it feels like there's going to be a physical explanation, a biochemical explanation that ultimately boils down to consciousness is a particular motion of particles surging through the particular structure inside your head that we call a brain. And that's all that it is. Now, saying that's all that it is not meant to denigrate. It's highly complex. It's rich. It gives rise to all of the experience that makes life worth living. But in the end of the day, it's only particles moving through a structure. And that's it.
I don't personally see how consciousness could just be the particles moving through anything. I see how consciousness could be generated by that in a very straightforward way. And I guess this gets back to the way I'm conceiving of consciousness. I like the way Thomas Nagel phrases it. The fact of consciousness is the fact that it's like something to be alive. right? It is like something to be you. You experience pleasure and pain. You have subjective experience. And I just don't, it could boil down to particles moving. The particles moving could generate consciousness the way a steam engine generates steam or something, right? They could be an epiphenomenon, kind of a product. Consciousness could be a product of this in a very straightforward way. This is called epiphenomenalism. But I think that's different from saying that which is kind of the view of Dennett, which is, I think, very much like saying consciousness doesn't exist. I mean, I and a number of people have accused Dan Dennett of believing that consciousness doesn't exist. It gets him really upset, so I encourage you to do that if you see him. But that's, so to me, this is the most, in a way, mysterious thing about reality, is that it is like something to be alive. And you'll note that it is what gives life meaning, right? I mean, the fact that people can experience pleasure and pain, that's why we talk about ethics, that's why life has meaning, and I think it's just notable that there is no satisfactory explanation. Because if you do view consciousness as an epiphenomenon, as a mere byproduct of the physical stuff, then the question is, well, what is it for, right? I mean, if when my hand goes into a flame, the fact that I withdraw it has nothing to do with my sensation of pain, but just the physical information flow, well, then what's the pain for, right? It has no functional significance. So in this scenario, which is a pretty common one, the epiphenomenal one, then the thing that gives life meaning has no function. Well, that's interesting. It's like a freebie. Thank you. Whatever's responsible for consciousness. It didn't have to be here. We could be these animals that behave exactly as complexly as we behave. We could generate speech with sound waves. It would hit the ears of other animals. It would roll around their brains and elicit more speech waves and so on. All this could be the case in principle, except this conversation where we're talking about consciousness. But in general, animal life could go on in this scenario, the epiphenomenal scenario, without consciousness. So the fact that it's here is, the thing that gives life meaning is like a freebie. That's an interesting basis for whatever you want to do with it, gratitude, whatever else. The alternatives, aside from the kind of Dennett view that, in my mind, is not tenable unless he's saying consciousness doesn't exist, which is even less tenable than the other thing, because it's definitely like something to be me. The alternatives to epiphenomenalism are almost contrary to science in a sense, because then you get back to some kind of Cartesian dualism where there's this ethereal stuff known as consciousness that's actually influencing the world. Now, I'm not here to rule that out, but I would note that according to this analysis, you've got two main choices. One is that the Cartesian one, things are much weirder than a scientific worldview would have you believe, because there's this ethereal stuff influencing the world. Influencing my behavior. The consciousness is in some sense generating behavior. And then the other scenario is, well, no, this is more compatible with science in the sense that you can explain all behavior without reference to consciousness, but in that case, it's like, what is consciousness for? That's kind of mind-blowing in its own right. So I just think one way or another, consciousness is just like the strangest thing in the world, and I think the thing that gives us most reason to believe we just may never figure this stuff out, because, or that science in particular may never figure everything out, because one feature of my private subjective experience is it's private. It's not scientific data. It's data that I say I'm hot or I'm cold, but the feeling of cold or hot itself is subjective, it's private, so it's not...
Just give Facebook a little time, my friend.
Yeah, well, no, they pick up on the cues. I mean, for them, what I say is enough. But anyway, that's my take on consciousness.
My question is for either one of you. What's the difference between artificial intelligence and natural human, artificial intelligence consciousness and natural human consciousness?
Well, I mean, there may come a point when there isn't a distinction, right? At this particular moment in time, I think it's pretty easy for us to point to what we would call a conscious being that emerged via the natural progression of the physical, chemical, biological laws that have been in place on Earth for the past 4.5 billion years, versus an approach toward intelligence that we have inside of a computer. So at a structural level, I think it's pretty clear that we can point toward the differences between them. But I, for one, think that that's just a moment in time. Far into the future, I don't think there's going to be a difference between them at all. They're all going to merge together, they're all going to meld together, and it's just going to be intelligence.
Okay, so one more.
This has been great, guys. I mean, that was one of the clearest discussions of the paradoxes of quantum mechanics I've ever heard. It was really terrific. So here's my question. And
No, you can stop there.
Thank you. And it's really a softball question. I'm curious, and I guess this is mainly for Brian because I know what Bob thinks. Do you think that with further research, physics and maybe other fields of science will dispel the mystery of reality? Do you think, so you guys have been talking about all these puzzles that have arisen from quantum mechanics itself. It seems to be making the world even stranger than it used to be back in the 19th century, let's say. Do you think that string theory or some other unified theory, some kind of maybe observational breakthrough, will suddenly make everything clear, not only to you guys,
It
to
won't
the
be clear to me.
professionals, but to everybody else?
Yeah, so I think it's an interesting question for the following reason. The clarity of which you speak depends upon the brains that are perceiving the explanation. And so to me, it's more a question of, will the evolution of intelligence, either natural or artificial or some melding of the two, will that be such that the brain power of that intelligent system is so penetrating that the explanations that we give feel intuitive? I think that's what we mean when we say, does it make sense? It's like, does it make sense in your bones? Does it make sense in some visceral way? And that, I think, is so dependent upon the beholder, right? I mean, if I take this and I throw it, I have a really good intuitive sense of the trajectory, so much so that I had to do no calculation at all. I put out my hand and I catch it, and most of us could do the same. That's spectacular. That is a deep insight into Newtonian physics. Without math, you all know where to put your hand to catch an object that I throw. Maybe we'll get to that point with the motion of electrons, or the vibrations of strings, or the nature of black holes, or vibrations in the fabric of space-time. Maybe our intelligence, augmented perhaps in some way, will give us that kind of deep intuitive insight into the nature of the world. So I don't think it's so much, will you physicists come up with explanations that will be so transparent that everybody says, okay, I've got it. I think it's really the question is, you physicists, go along what you're doing, figure out as close as you can get to the deep laws of reality, and then hopefully intelligence augments in some natural or artificial way so that there's a melding and meeting of the two.
Okay, so we shouldn't keep you here a lot longer, so maybe what we should do is go around to 3 people, and they should just go ahead and ask the questions. I'll write them down, and then we'll answer them, and that'll be it.
What do you think about Jordan Peterson's claim about? I mean, what do you think about Jordan Peterson using religion or like biblical stories against science?
I have no idea who that is. Should I?
You should. You totally should.
Yeah.
Jordan Peterson's a fascinating figure.
Please, I'm all ears. Go ahead.
Well,
quickly.
maybe I'll say 3 words about that. And so we have 3 questions left to go because Brian won't have anything to say about that.
Hi, Professor. Earlier you mentioned that you are not very convinced by many worlds.
I'm sorry, one more time?
Many worlds
Yes.
interpretation, and because it just follows from math, and it doesn't describe the reality we seem to know. But you are also, I was going to use proponent, but you're also working on string theory. But string theory also requires some kind of, the mathematical formalism of string theory also requires our reality to be, for instance, more than three-dimensional in space-time. So my question is, in what sense do you think string theory is more realistic or real compared to many worlds theory? Why it's more like
Yeah.
yeah.
So should I clarify?
Well, let's go ahead. Let's go ahead and take
Yeah,
the other two,
Right.
for the sake of time.
Yeah. You are writing it down because I will forget.
Yeah. Keywords.
Sorry, just seems like a unique opportunity to ask each of your individual perspectives on why there seems to be such a long and strange affinity between Buddhism and quantum theory. Going back to Planck and Bohr and Oppenheimer, Heisenberg, it seems like, especially with the two of you, if you could comment on that kind of weird corollary.
So Buddhism and quantum mechanics. Okay, so one more.
On the heels of that question, actually, I was wondering if there's a perspective on the history of the Christian mystics in terms of perception of the sense of direct experience of God, of the silence of one's mind for 20 or 30 or 40 years, the plasticity of the brain. Can there be a conception within quantum physics that a certain individual who has had some sort of discipline or practice of mindfulness in some tradition for an extended period of time might have an awareness or perception of reality that is different than a mathematical formula can produce, and where that might fit into all of this?
Okay, so you've got that question in your mind?
Better start there.
You better start there.
Yeah. Are we ready?
I think so. Should I say something about Jordan Peterson? I mean,
Oh, yeah, go
Jordan Peterson, for people who don't know, he's this Canadian psychologist who's kind of burst on the scene in an interesting way by violating what he calls political correctness in a very spectacular fashion, and it being on video and going viral. But it turns out he's long written about religion. I guess I would say that, so far as I can tell, it's a little bit like Joseph Campbell with a little, taken a step further. In other words, a real emphasis on drawing on archetypes of mythological archetypes, and applying them to your life, or religious archetypes and applying them to your life. I gather one thing he does is say, okay, there's these three parts of the mind, and I don't know what they are, and I don't know, I doubt I'd buy that division of the mind, but in any event, he says they're like the Trinity. That's like the Father and the Son and the Holy Ghost. And this has resonance for certain kinds of people. I would guess mostly Christians in that case. And I think that's a certain amount of the religious part of his worldview. It's interesting to see what it is that appeals to modern seekers. And then aside from that, I mean, his take-home message is get your act together. Clean your room is his famous phrase. You know, you can't save the world. I guess it's like, who was it, Voltaire, who said tend your garden, but anyway, you know, clean up your own backyard. He's an interesting phenomenon. I shouldn't claim I know any more about him than that, so I'll stop there. So do you want to pick up on the Christian mystics?
Yeah, so, yeah, sure. Let me frame it the following way, and I don't know if we have time for follow-up, so I don't know if this is going to be useful or not. But I am a firm believer that at rock bottom, as we've been discussing, it is some mathematical law, or perhaps even some law framed in a different formalism too, that undergirds reality. So let's take it to be quantum mechanics, because that's our most refined version today. And I do believe that that is it. There's nothing else needed from the outside. There's nothing that we need to inject into that structure to have a complete description of what reality is. Now, having said that, I also am a firm believer that when you engage with reality, there are different levels at which you can engage with it. right? You can engage with it at the level of particles if you're a particle physicist and maybe an aficionado of those kinds of ideas. But most of us don't live down at the level of particles. Most of us engage with the reality at higher levels. And at those higher levels, the vocabulary, the language, the ideas that are relevant to have a full description of what's going on need not make any reference to the underlying particulate language that we particle physicists use. So some would say that that means that you're connecting with new things, that there are new ideas that are coming in. If you train your mind in one way or another, maybe you're better attuned to channeling those qualities of the universe. I don't use that language because I do think that underneath it all, it's just the particles acting themselves out in spectacularly complex ways. But I am a fan of being willing to change my perspective, change my language, and make use of the more familiar concepts when you're trying to describe familiar life. I would never take a baseball and try to, Aaron Judge hits it, right? I would never try to use quantum mechanics to describe the motion of that baseball. I mean, there are 10 to the 23 particles in there. To try to apply Schrodinger's equation to that, I mean, it would take that quantum computer to the nth degree to try to actually calculate using it. It'd be ridiculous. So instead, you change perspective, you use Newtonian ideas, which are a pretty good approximation of what happens to the baseball. Just scale that up, and it applies to the happenings of everyday life. It can go further than that as well. So I don't think there's any channeling. I don't think there's anything else to be found from that perspective. But I would just shift it a little bit and say, hey, the poets, the novelists, the composers, the artists, they are giving us deep insights into the world that you don't need to be a particle physics to grasp, appreciate, and grow from.
So the next one, and these are going to have to be the last ones, the ones that have already been asked. Buddhism and quantum mechanics. Why
was
are
that again?
Well, why are a number of quantum physicists inclined toward Buddhism or maybe Eastern mysticism more broadly?
I mean, you wrote the book, man, so I should toss it to you. But I will say one thing. I did an event. I don't know if we discussed this any time. I did an event some years ago in Houston, I think it was, and the Dalai Lama was there, part of the event, and so we had a public conversation. And in that public conversation, I asked him, there are all these books that speak of, Eastern religion and quantum mechanics, and you know the ones I'm referring to, and so what do you think of that, Dalai Lama? And he said, when it comes to fundamental physics, we need to turn to you guys. We need to follow what the physicists tell us. He said, when it comes to consciousness, we have something deep and important to offer. Mm-hmm. But when it comes to quantum mechanics and fundamental physics, you guys lead the way and we will follow you.
Yeah. I don't think I have a good answer. Now, Erwin Schrödinger was something of he was inclined toward this, right? I mean, his book, what is the little book that is paired with Mind and Matter? He wrote a little thing called Mind, and then the more famous book is paired with it, but what is it?
There's What is Life?
What is Life? Okay, so What is Life and Mind and Matter are paired together, and Mind and Matter is very kind of mystical, and What is Life is a very profound book. I mean, and I don't know. I mean, the first question I'd ask is this not somewhat true of scientists generally? Could you not find other scientists who are inclined this way? In which case, maybe part of the answer is that they were disabused 100 years ago of what you might call primitive conceptions of a deity. They were entering the modern world maybe sooner than the average American, and that the version of Buddhism that made it to America, which is actually the part that's stripped of the religion that's actually part of Buddhism in Asia, but anyway, meditation and the philosophical part of Buddhism, very appealing. I'd also say, I think, the philosophy of Buddhism is very sophisticated and, in a sense, very scientific in spirit. There's a tremendous emphasis on the pervasiveness of causality, believe it or not. And that's the reason that, the notion of the self is cast in doubt. That's one reason, is because there's an awareness that what I think of as myself, this autonomous thing that's doing the deeds and thinking the thoughts and making the decisions, it's actually being influenced all the time by all this stuff from my environment, and maybe it's better described as a mediator than as an autonomous thing. So I can think of reasons why Buddhism would be appealing to scientists. I'll think about the quantum physics thing. I mean, was David Bohm a little mystical?
Some would certainly say that.
Yeah.
You know.
So I don't know. It's a very good question. I don't have an answer. The last question, which is for you alone, is about many worlds in string theory.
Yeah, sure. So when I noted that many of us resist the many worlds interpretation as currently formulated, I definitely framed it in the guise of it violates our sense of reality, it violates our intuition, especially when it comes to the intuition about probability. But that really has a mathematical incarnation, even though I use that everyday language. And again, not everybody agrees with this, but what's difficult for us to make sense of is how do you even mathematically define the notion of probability in a many worlds interpretation? Some believe they have solved that problem. Others are more skeptical that that solution really is what it purports to be. So when it comes to many worlds, it's although I may frame it with intuition and our sense of what the world should be, it's really a brute force mathematical issue in the laws of quantum mechanics. So when we now turn to string theory, and there are some strange counterintuitive qualities, some of which you point out, that there may be more than 3 dimensions of space, and there are many other weird things too. I see it as a completely oblique direction relative to the critique of the many worlds approach. I'm perfectly happy to go in strange directions so long as the mathematics is taking me there. And the mathematics of many worlds, I don't find it taking me to many worlds as yet. But the mathematics of string theory is taking us to ideas of extra dimensions, so we follow and see where it leads.
Okay, so I'm afraid that should be about it. Thank you. Let me say 2 things. Brian and I have to actually be somewhere at 8, get in a car, so I'm afraid, I'm sure a lot of you have other questions for him. He's not going to be able to stick around. So what I would recommend is you go to the World Science Festival in May and try to corral him there. I have no idea whether it's possible there, but it gets me off the hook tonight. So, and finally, I mean, I know you've already given us 1 round of applause, but Brian has really exceeded my already high expectations. And for somebody who hasn't been getting much sleep, he's been incredibly dynamic, articulate, clear, profound, and so on. So let's thank him one more time. This is great.